I definitely care about my students because that's being recorded right now.
Jerry was laughing because he cared
But no. I like the cream stick.
Oh, which was the maple or the chocolate?
I don't care. I'm a non-discriminatory cream stick lover.
I like cream sticks are top tier.
Yeah.
I like cream sticks a lot.
Really? See, that doesn't exist. Too sweet does not exist.
You can skip through
Brownies, brownie batter. She's a brownie batter donut. Because it's like brownie batter going within the donut. All right. So, somebody asked me, one of my Algebra 1 students asked me, so what is calculus? Like, what do you guys learn in calculus? And so it's a lot about finding the derivative. And they're like, well, what's that? I said, well, like a curve, because we've been studying parabolas. I said, like a curve, like it basically is finding the highest point, the lowest point of that curve. And they're like, oh, well, what is it useful for? And I said, well, actually, I teach that today. Optimization problems. That is like the biggest use of calculus, in my opinion. Yeah.
Speaking of Algebra 2, did you ever hear back from that Jerry kid?
No, not yet. Jerry.
Isn't his name Jerry?
Yeah. Shout out, Jerry, if you're watching. Shout out. No, hey, you never know. All right, so section 4.7 is all about optimization. We're not really going to do anything new today. We're not learning any new content today. All we're doing is applying what we know to real life situations. Okay? Applying what we know to real life situations and using what we know about derivatives to answer that. Okay. So let's take a look. The methods we've learned in this chapter for finding extreme values have practical applications in many areas of life. A business person wants to minimize costs and maximize profits. That would be finding the biggest possible value, the local maximum, or the absolute maximum, or the local minimum, or the absolute minimum, minimizing costs, minimizing hours worked, maximizing profits at those locations. A traveler wants to minimize transportation time. Fermat's principle in optics states that the light follows the path that takes the least amount of time, so minimizing time, maximizing area, minimizing cost, whatever. Whatever you want to try to make something the smallest or biggest value it could possibly be, well then it must occur at one of those extreme values. Thinking all the way back to Honors Algebra 2, we did problems that were called linear programming, where we gave you a set of constraints and asked you to, based on those constraints, find the biggest or smallest possible value of a given function. And there was one on there, I still remember this. It kind of looked like this, and then the diagonal line coming through, and then we had like a shaded region in there, right? And we learned that the vertices of the feasible region were where that maximum or minimum point could exist. Now, basically what we're doing there, we know that derivatives of these functions happen at these kind of kinks in the functions, right? They happen at extreme values or maximums or minimums or places where there's corners, right? So it almost makes sense now seeing this on, with hindsight, saying, oh yeah, I bet at corners, at places where these things bend, that's got to be one of the one of those maximum or minimum values, because that's where the derivative would not exist for those things. So the goal of this stuff is to either maximize or minimize a certain function, okay, a certain objective function. In solving such practical problems, the greatest challenge is often to convert the word problem into mathematical optimization problem by setting up the function that is to be maximized or minimized. Now, they give this outline of what they, would suggest to how to set up every problem. Okay, this is the outline that they suggest to set up every problem. So first thing, understand what's going on. The first step is to read the problem carefully until it's clearly understood. Reread it 2, 3, 4 times if you need to. Ask yourself, what is unknown and what is known? What is the unknown? Define it for yourself. What are the given quantities? What are the given conditions? What are the constraints of your problem? What do you know about the situation? Second thing, and I always do this, draw a diagram. I am a visual person. If I can see it, I can try to apply it and try to apply equations to it. Okay, try to draw a diagram. Next, introduce notation. And my algebra and calculus teachers were, I don't know, it's always been ingrained to my head to define your variables. Define your variables. And that's going to be extremely important when I grade your work. Because if you introduce a variable and I don't know what variable you're using and I don't know what that variable stands for, and it's not clear within the problem, like obviously, you set s equal to speed or you set t equal to time. That needs to be very clear if you set that variable like x equals time. I need to know what x is if you define x to be time. Yeah.
So you're just saying to like put a key at the top or something?
Yeah. My teachers had always said to say, let x equal, let y equal, let a equal, let b equal, and just note it within the context of the problem. So introduce notation. Assign the symbol quantity that is to be maximized or minimized. For our purposes here, they call it Q. Let symbols A, B, C, X, Y, whatever for other unknown quantities, and label the diagram with those symbols. It's important to, within your diagram, label what you've assigned to each piece. It may help to use initials as suggested symbols for example, A is area, H for height, T for time, whatever. Make it fit the context. Next thing, express your function that you're trying to maximize and minimize in terms of some of the other symbols, and then also including that in step 5. If Q has been expressed as a function of more than one variable, if you've got, say your area is length times width, you only want the area expressed as one of the two variables. Okay? You want to try to, using another type of equation, figure out, okay, can I define length in terms of width somehow? Is there some other information going on that I can combine those pieces? Okay. Then use these equations to eliminate all but one of the variables. Now, after that, we're going to use calculus. We're going to say, okay, after you've got the function that you're trying to maximize or minimize, that's when you say, okay, I'm going to find the derivative. And because the maximum or minimum value must occur at the derivative. Now, if it's an interval, you can use the closed interval method that we learned early on in this chapter. We know that the absolute maximum or minimum of a closed interval has to either occur at one of the endpoints or the critical points. Okay? If it's not a closed interval, well, then we just kind of have to reason it through based on a reasonable domain for whatever we're given. Okay? All right. So let's just start. We're going to get through as many examples as we can, and whatever we have left over, we're going to finish on Monday. Sound good?
Yep.
Perfect. All right. Example 1. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along that river. What are the dimensions of the field that has the largest area? Right. We've almost done this with implicit differentiation. And we can use, it's funny you bring that up, we can use implicit differentiation to do this as well. All right. So I like to say what is being maximized or minimized in words right off the bat. So what am I trying to maximize? Area. I want to maximize area. Right? That's the function that I'm going to end up finding the derivative of. I want to maximize area. Okay? All right. Let's draw our diagram. We've got this river, and then we've got our fence, a rectangular fence, which we do not know the dimensions of. let's let x equal the length and let y equal, we're going to call this the width. What would you call that? Would you call this long piece the width or the length? Really? Yeah, I would call that the width. I'm just wrong. Oh, okay. Sorry. So I've got x, because it's got to be a rectangle, that's my restriction there. It's got to be a rectangle. I know that those two pieces on either side are going to be x, and then the long piece there is going to be y.
So like if you turned it, would you switch between?
See, now we're creating this stuff, right? So it doesn't really matter in the end. Once we're done with this problem, our answer would be the same no matter what. So how you set up the problem is going to be different based on how you're thinking about it. This is just how I think about it. All right, so we got x on the top, x on the bottom, y there. Now, notice that the area of this thing now is just x times y. I can't find the derivative of that yet because it's two different variables. I mean, I could do implicit differentiation, but we really don't like implicit differentiation. And there's other information I can use so that we don't even have to do that. All right, so let's take this 2400. Isn't that the other piece of information we haven't even used yet? What do we know about that 2400? Well, that's the amount of fencing that I have. Okay, well that's equal to 2x plus y, right? It's almost the entire perimeter, but I can exclude one of the side lengths because it's next to the river. Well, isn't that equation really easy to solve for y? 2400 minus 2x is equal to y. So what we've done here is we've created another equation that we can solve for y, and now we're going to plug it back in. Meaning, my area is now x times 2400 minus 2x. Or in other words, 2400x, oops, not 24,000. 2400x minus 2x squared. That's the area. Now, it's important to think about the domain here. Is this truly a closed interval? Because now I'm either going to try to reason this through as a local maximum or minimum, or use absolute maximum or minimum, right? Local maximum or minimum would be if I'm looking at the closed interval method, because I can find one side of the function, the other side of the function, and find the critical point in between. Absolute maximum or minimum would be, I would have to reason it through in another method. But the domain is restricted, isn't it? What's the smallest possibility for x? 0, right? If we had no length and only width. What's the biggest it could possibly be? What if I use all my fencing? Well, I've got to have two sides of x, right? Two sides. I don't have 4,800. 1,200, right? 1,200. If I had used all of my fencing just for x's, 2,400 for just the two x's, the biggest x could possibly be is 1,200. So that's my domain of this. So I can use the closed interval method. That's a closed interval. I'm going to find my derivative of my area. Because that's in that critical point. Once I find the derivative of my area function, the critical points of that derivative is where the maximum or minimum could occur. All right, so let's find the derivative. We're going to say f prime of x. You could say a prime if you wanted to. 2,400 minus 4x. Right? And I set that equal to 0, because that's where the critical points could occur. All right, add over the 4x. divide by 4, 600. Okay, closed interval method says make my table, my x and y table. So if x is 0, I'm not really making it, an xy table here. But if x is 0, what's the total area? What's my output? 0. If x is the biggest, 1200, what's my total area? Still would be 0. All right, so if x is 600, now I could right away calculate what my y value is going to be, right? Like if I don't know the y value here. So if it's 600 comma, what would the y value be? Yeah, because we got it here. 2400 minus 2x, right? So 2400 minus 1200 would be 1200. Right? So what's the total area if my x value is 600? Well, the total area would be 600 times 1200. $720,000. Right. I should do a different notation there. I should say area instead of y.
What do we multiply 600 and?
1200.
Okay.
Because I'm trying to maximize my area. So the biggest area that I can have there is 720,000. And where does that occur? That occurs at 600. So what are the points there? Well, then that means that it's 600 feet by 1,200 feet. Those dimensions would maximize my area. What was I really plugging those into? I was really plugging those into this area function right here. 2400 times 600 minus 2 times 600 squared. In other words, I was looking at, okay, what was my y value? And finding the area based off that. So what did we do there? We used our derivative to find the maximum or minimum value to find the maximum area possible using the given conditions from the problem. Yeah.
Will we always do the closed interval method?
No.
Oh.
Only when it's a either it's like a real life example that has endpoints, like I can't go into negative, so it would be 0, right? But if it's an abstract problem, like we'll see here in a couple problems, you could go into possibly having negative numbers, so you have to work with that. Yeah.
Okay, I got lost. What if you write down the 600, 1200 points, and then you went back and wrote?
And then I found the area. Yeah.
How would that give us the answer?
What I'm doing with this table is plugging it into that function, right? Because I'm trying to maximize that function. So I find the endpoints and the critical points and plug them into the function to see which one gives me the biggest amount, right? And I knew that, my two endpoints, 0 and 1200, if I plug those in for that, that's going to give me 0, right? If I plug 600 in for this, that's going to give me 2400. Right? What I did here was because it was really simple to do, I just found, well, the x value is 600, which therefore means that the y value is going to have to be 1200. Because it's just a really simple thing to do. 2400 minus 1200 would be 1200. Yeah. And then the area based off of that is just x times y, way back at the beginning, which is just the area of a rectangle. So I just used that to find the 720,000. Yeah. A lot of different ways you could think about it. Yeah. Shall we do another one? That will do anyway. Yeah, this whole section is all word problems. Yeah. I will tell you that like like, I heard somebody say this is like AP stuff. Yeah, a lot of, I know, I get it. A lot of the AP test is a lot of word problems like this. Like figuring out your way around, like figuring out how to maximize, how to minimize, and whatnot. Less algebraic, more conceptual like this. All right, a cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. Okay. So what do I want to minimize here? I want to minimize cost, but how do I minimize cost? I find the smallest surface area I possibly can. Right? That will minimize cost. Find the smallest surface area. So yeah, while we can say we want to minimize cost, minimize cost, I have to do that by minimize surface area. All right, so let's write out what we know about this cylinder. I would assume that I want a top to my can. I want all surface area. It's not like I have to exclude the top or anything like that. I want top, bottom, and all the sides. We know that the surface area of a can is 2 of the bases, 2 pi r squared, plus the area of the outside part, which is really a rectangle, where you have the circumference of the bottom times the height. So there's my surface area formula. That's what I'm going to eventually find the derivative of. Now, the problem is I've got radius and height. And both of those things could vary, right? I could change the amount of radius, I could change the amount of height, and it will change the surface area of the can. So I've got 2 variables working against each other. Let's try to eliminate one of the variables by using this first statement here. Now, they tell you in the book, within the context of the problem, you need to know this conversion factor. You need to know that 1 liter is equal to 1,000 cubic centimeters. Did you guys know that? I didn't know that. And I was like, I tried to do the problems without looking at the book's answers. And I'm like, well, how do I change liters into linear thing? So 1 liter is 1,000 cubic centimeters. Changing from liters into centimeters. All right. So how does that help us? Well, I know that the volume of this thing is pi r, what is it? Pi r squared height. I was going to say pi r squared height. I was right. Pi r squared times height. Well, if the volume is 1 liter, it's 1,000 cubic centimeters. So this is 1,000 is equal to pi r squared h. Now at this point, we just have to decide which variable we want to eliminate. Do we want to eliminate x's or r's, or do we want to eliminate h's? I did the book, The Office. I can name that tune in 3 notes. The book solves this equation for h, so I'm going to do the exact same thing. So I'm going to divide by pi r squared. So 1,000 divided by pi r squared is equal to our height. Our volume in cubic centimeters divided by pi r squared is equal to our height. The reason we needed to do the conversion factor is because my radius and my height are all going to be in linear length, not volume type dimension, right? So we wanted to change it from liters into centimeters. All right, so now we know this is my height. So let's go plug that in. We know that my surface area is now 2 pi r squared plus 2 pi r times 1,000 divided by pi r squared. All right, so that means we can eliminate the pi and the r and this exponent there. Okay, because we're multiplying there. So let's reduce it down. Surface area is equal to 2 pi r squared plus 2,000, 2 times 1,000, 2,000, divided by r. And that's about as reduced as we can get for the surface area formula. So let's find the derivative. Let's find the derivative of that. Now, to find the derivative, I think it's going to be easier. Rather than treating it like a quotient, let's just treat r in the second term to be a negative exponent. Sound good? So we find the derivative. I'm going to call it f prime of x of r, I guess. I don't know. I'll just keep the same notation. 4 pi r minus 2,000 times r to the negative second power. I bring the negative 1 down in front. That's why it turns from positive to negative. And then decrease the power by 1, negative 1, negative 2. Yeah.
Why didn't you do any product rule on the 2 pi r?
Because the only variable here is the r. 2 is a number, pi is a number.
Okay.
So I can just bring it down in front and multiply. So let's rewrite it a little bit. So f prime of x is equal to 4 pi r minus 2,000 over r squared. And now I'd like to get it as a common denominator. I'm going to make r squared my common denominator. So to do so, I'm going to multiply this by r squared over r squared, which will get us 4 pi r to the third over r squared minus 2,000 over r squared. Just trying to reduce it a little bit. The common denominators to subtract. So that's equivalent to, we got 4 pi r cubed minus 2,000, all divided by r squared. That's my derivative. Now, think about the, yes, go ahead.
What's the numerator of that red?
R squared over r squared. Yeah, I'm just getting common denominator, multiplying by the denominator. What, you can't read my handwriting? Looks like a V, doesn't it?
Yeah.
That's right. All right, so now let's find the critical points of this. Now, let's think about the domain. Can I have negative radius values? No. So my interval is between 0 and, what's the biggest it could possibly be? I think we don't even need to worry about that. And I'll show you why. But the smallest that could possibly be would be 0. Like, so I have an end cap on my left side, basically. Now, when I find my 0 here, my critical points would be where the derivative does not exist, so 0, r equals 0, or where my numerator equals 0. Because that would make the whole function, whole derivative 0. Add over the 2,000. Question. Divide by 4 pi. And then I cube root it. Now, if you look in the book, they keep it in exact terms. So their answer is r is equal to the cube root of 500 over pi, but I'm going to use a decimal. So r is equal to 5.42, thereabouts. I just cube root 500 over pi. Right? 500 over pi gets us that. Cube root of that answer is about 5.42. That's where I got that number. Okay, now, let's take a look at our number line. Here's 0, here's 5.42. Now, does anything exist to the left side of 0 in our purposes? No. This does not exist over here, so I don't even need to worry about it. So let's check everything for the left of 5.42 and then to the right of 5.42. Well, if I go to the left, I'm plugging this back into my derivative here. If I go to the left, that's going to make the top negative and the bottom is going to stay positive. So negative divided by positive would be a negative. And if I go to the right, if I plug in, say, 6 or something, that's going to be bigger than 2,000. And so it's going to be a positive divided by positive. It's going to be positive. Will this turn back again negative? Never. It will not, because it could only possibly happen at the critical point. It could only have another turning value, another maximum or minimum, if I had another critical point of that derivative. And I don't. Okay? So that's why I'm saying there is no real upper boundary that I would need, because it's going decreasing then increasing. And if I want to find the smallest possible value, it's not going to turn back down again. Okay? It would have had to have happened at one of the critical points. So I know for certain that this will not turn back again. So this is the only minimum value. The only one. Okay. It will continue to be more, get bigger and bigger and bigger and bigger to the right of 5.42. And I don't even care what happens at 0 or to the left of it, because it doesn't exist there. All right, so my only minimum value is 5.42, so that means my my radius is 5.42. Okay, that's where the minimum will occur. And what is the height? What's it say? Find the dimension. So I need to figure out the height. The height is defined to be 1,000 divided by pi r squared. That was just from above. So we plug that in. 1,000 divided by pi times my radius, 5.42 squared. Right, 1,000 divided by pi r squared. It actually gets me 2 times what I had for my radius. My height is 10.84. Computer's going a little slow. That's an 8. That's a really wonky 8. Sorry about that. I find that the more I write on a page, the more glitchy it gets on that page. Okay, so those are the dimensions. Radius is 5.42. The height is 10.84. That's all it asked me for. Could I go ahead and then find the surface area if it really wanted me to? Sure. You know, maybe this problem gets a little bit even more involved and said, okay, the cost is this amount per cubic centimeter. Find the total cost of each can. You know, you could then go even further if you wanted to. But for our purposes, we'll stop here because that's all they asked us for. Does that make sense? Okay. All right. We obviously won't get through another problem in 10 minutes, so we'll pick up there on Monday. Sound good?
Donuts.
No donuts.
I have a gift card with $1.82.
Wow, that'll get you like half a donut.
Yeah, I'll give it to you.
That's okay.